Okay, welcome back. We will pick up from where we left off and build on it. Keep in mind the building blocks that we have developed, and because now this section it's more about putting all the pieces that we have developed together. So here is the first figure that would like you to keep in mind. So here is a M channel multi-carrier transceiver. Multi-carrier transceiver, okay, and we will use the following notation where we say minimal. That means it is optimal in some sense, the fact that we are not going to use any additional bandwidth, no redundancy built into the system. So the structure of this is going to be as follows, because this is our baseline reference diagram. I have M signals S0, S1 through Sm minus 1. We would like to process this, combine them into a single signal, pass it through the channel and then recover it. So the process of combining, we are going to draw it as upsampling by M, no redundancy in this particular structure. This is our baseline structure, dot dot dot, each of these filtered by a appropriate filter, either low pass or band pass, F0 of Z, F1 of Z, Fm minus 1 of Z. Combine these signals by adding. Dot dot dot, no delays because we are just basically adding the outputs of the filters. Let me give some labeling so that we can analyze it. U0 of n, U1 of n, Um minus 1 of n. The output of this is the signal, let us call that as x of n. Here comes the channel. We have not made any assumptions about the channel. In the general case, it will be a dispersive time varying channel. So if you want to describe it, this would be a multi-tap, that means we will have C0 plus C1 Z inverse, C2 Z minus 2. So multi-tap model, this is what will capture the inter-symbol interference that will be introduced by the channel. Now one aspect that we cannot control, but we have to include or at least mention in the channel model is the noise. Let's call it as eta of t. We are really not going to do much about the noise, nothing we can do. It is just an impairment that will make the affect the quality of the signal, but other than that. So now that is the pass through the channel. Now at the other end, we must start the recovery process. So the first step is to pass it through a bank of filters, H0 of Z, H1 of Z up to Hm minus 1 of Z, Hm minus 1 of Z. Since we have to preserve the sampling rate, each of these sub channels is downsampled by a factor of m, downsampled by a factor of m, okay, and the outputs are labeled as S1 hat, S0 hat of n, S1 hat of n, Sm minus 1 hat of n, and the role of a multi-carrier or a multi-carrier transceiver is to have S0 hat to be as close to S1 as possible, S0 as possible, because that is what you have done. You have been able to combine M signals, transmit it through the channel, and through the processing at the other end you have been able to separate it out and then get back the original signals. So, this would be the a minimal transceiver for a multi-carrier system. In a multi-rate DSP context, we will call it a transmultiplexer. In communications or in other contexts, we could call it as a multi-carrier transceiver. So, this is a transmultiplexer structure primarily, because you have the synthesis stage where you combine signals to produce a frequency division multiplex signal, and then you do the reverse in the other end. Okay. So, the synthesis filters, there are M filters, synthesis filters. So, this would be the complete description. You will have f naught of z all the way to f m minus 1 of z. These are the synthesis filters. There is a channel which is a multi-tap channel. We represent it as C of z. There is additive noise which is given by eta of t, eta of n. Let's not mix continuous time and discrete time. Let me just change this to, okay, everything we will represent it completely in the discrete time. Eta of n, that is the, and then we have the analysis filters. There also can be called as the receiver filters. Analysis filters h naught of z, h m minus 1 of z, that is your analysis filter bank, and your inputs to the multi-carrier system. Inputs are S naught of n all the way to S m minus 1 of n. An important observation or as a comment which is useful for us to keep in mind. Now, these signals can come from m different users, that is possible. M different users, you can think of them as signals of different users. At the same time, you can also think of it as the user data from a single user after, from a single user after the serial to parallel conversion of dimension m. Okay, so that is also possible. So, if you want to think of a high data rate system, then you would think of it as one user's data which I split, transmit through the channel, and then recombine and recover it at the other end. So, both again, how you got S naught, S1, Sm minus 1 is not as important, but again it is something that we just introduce. Okay. So, if you have this picture in your mind, write on the following observations or comments. We call it a perfect transmultiplexer, just like we had perfect reconstruction when you had analysis followed by synthesis. We can have a perfect transmultiplexer under the condition that C of z, when C of z is equal to 1. That means the channel is not dispersive, it does not do anything. Under this condition, if you can show, then when Cz equal to 1, then Sk hat of n is equal to Sk of n. Okay, so if there is no channel, if you can show that the input outputs are related in such a way that the whatever you fed in at the input came out at the output for all the channels. Noise is something that we just say that, okay, this that is why we do not say, we can say maybe you can add it as plus noise. Okay. So, some nk of n, but really there is not much we can do about this. So, we are saying that in the, if you ignore noise, will you get back the original signal. So, k greater than or equal to 0, less than or equal to m minus 1. So, basically it will be the input signal with some corruption by the noise, but not any other type of, however, this is not a realistic assumption, because typically C of z is a multi-tap filter. So, therefore, now let me ask you one quick question. Is x of n a narrowband signal or a wideband signal? wideband, because you have combined many narrowband signals. Okay, keep in mind. So it is a wideband signal. Wideband signal means it will see because a wideband signal has got very high time resolution, reciprocal of the bandwidth. So therefore it will actually see a multitap filter. So C of Z is a multitap filter, and which means that the signal X of n is going to see a frequency selective fading channel. Frequency selective fading channel. Okay, so that is a very important consideration, and this is what makes the transmultiplexer design difficult. Okay, because you have a wideband signal and it is passing through a dispersive channel, and this is when you go back and ask the question, hey, wait, you need to help me solve the equalizer problem, because otherwise I am going to have a real tough time for a transmultiplexer, the equalizer problem. Then you go back and say, hey, you know what, by the way, if this was a set of narrow carriers orthogonal to each other, if you constructed X of n in that fashion, which is what this structure can give you if you construct it correctly, then the C of Z may not be as much of a problem, because each of these narrow band signals will see a flat channel and I can design for you an equalizer. So this is where we are coming from. So basically, if you just took a multi-carrier system, yes, there is a challenge with the channel, but if you design it in the fashion of orthogonal carriers, then we can take advantage of that. Now the filters that we have to involve in the design of the transmultiplexer, that is F0, F1 to Fm minus 1, H0, H1, Hm minus 1. Now these become very critical if you have a minimal transceiver. So that is where we introduce redundancy. So we say that, okay, in this minimal transceiver, if we are permitted to introduce redundancy basically means that we will do upsampling by a factor of n, upsampling and downsampling by a factor of n, where n is greater than m. However, there are only m synthesis filters. Okay, so m synthesis filters, that part has not changed, but we are using a higher sampling rate. So therefore redundancy has come in. This is what we have talked about. So this also means the fact that you have n is that for transmitting m symbols, okay, m symbols, in a minimal transceiver you would have used m samples. Now we are using n samples. Okay, so this is where the redundancy is sort of coming in. So instead, let me just maybe make it very clear, saying instead of m symbols, m samples. Okay, so that is where the redundant transceiver is sort of building it. So this basically gives you a clue as to where the redundancy is coming in. I have n minus m additional samples, or let me call that as the redundant samples, okay, within quotes. These are the ones that are introducing the redundancy for me for each per set of m input samples. That means when I want to transmit one block of m vectors, I should have used m samples, but now I am using more number of that. So this can also be interpreted in the following way. It says that what is my transmission rate of my system. So the transmission rate or the throughput rate, transmission rate, if it were a minimal system, the number of symbols per second is 1 over Ts. That is the number, the Ts is the duration of one symbol, the number of symbols per second is 1 over Ts. Now each symbol can carry b bits of information, so into b, correct, and there are m channels. So, MB by TS would be my throughput, that is what that would be my the throughput that we would achieve. Okay. So, this would be effectively the throughput of a minimal system. Okay. Now, did I get that correctly? 1 over Ts, that is correct. No. Wait. Ts is the I have to see how we have defined Ts. Ts is the input sampling rate. So, therefore, I would okay. Actually, on the this has to be because once you go to the after combining it, here it will go at a faster rate, right, because of the interpolation it will be Ts over M. So, so this Ts is at the input rate. So, basically B times Ts. So, this would be the rate at which the information is going across the channel. Now, if I look at the case where I have redundancy, with redundancy, I will get a factor less than 1, and that factor will be M over N into B over Ts. Okay. So, that would be the this Ts is on the channel, the channel signaling rate. Okay. So, basically I would use N symbols, but I would have effectively transmitted only M information bits. So, which means that I would get a reduction compared to the minimal system. So, the redundancy basically you pay a price for it. The other aspect that we just have to keep in mind, again just as a comment, your A to D converter at the receiver side and the D to A converter both are running at a higher rate because you have done a higher sampling rate, operating at higher rate. So, in other words, the transceiver with redundancy has got some price penalty, but again it is one thing that helps us build the practical system in a good way. So, higher operating at higher rate. Okay. These are sort of general comments. So, let's go back and combine the information. So, what are the types of distortions that we will encounter in this particular system? So, here is a visualization of the system. I would like you to comment and note down the distortions. So, the possible distortions that are present. Distortions are in the Sk hat of N, where the SKs are the Sk hats are the outputs. So, the distortions in Sk hat of N. The first type of distortion is what we call as inter subchannel interference. Inter subchannel interference. Okay. Now, this means that Sk of N is being affected by Sk minus 1, Sk minus 2, because they are different subchannels. If they can interfere, now how can they interfere? Because when we constructed the combined signal, remember there is a mixing of the multiple carriers. So, at the receiver, if I do not recover them cleanly, then there could be an interference between the different subchannels. Okay. So, basically what we say is that Sk hat of N is affected by Sk of N but that is the correct thing because that is the input, and some S m of n where m not equal to k. Some of the other sub-channel signals also are showing up. The second type of impairment is what we call as the intra sub-channel interference. Supposing you have designed your system such that there is no inter sub-channel, these different sub-channels are not mixing, you could still have what is called as an intra sub-channel. So, which means that Sk hat of n is affected by, or is it depends on Sk of n and Sk of n minus m, where m is not equal to 0, some symbols either before or after. Okay, and this can happen if there is some kind of a filter in between the input and the output transfer function, and that means there will be some mixing of this, there will be intersymbol interference. So, this is a form of intersymbol interference. So, within itself it can create interference. This also is a undesirable part, and we want to control that as well. So, having all of these picture in mind, so let me summarize. This is the multi-carrier transceiver. If I want to introduce redundancy, we will change m to n, where n is a larger number, and then we have to design the overall system such that we pay the additional price of redundancy, but at the end of the day, can we get rid of inter sub-channel interference, can we get rid of intra sub-channel interference, and then build the system. So, this is where the multi-rate part, now we come in, bring it in, and then actually help us design the systems.